Hello, my name is Juan Diego. Today I'm going to explain economic operation of a fluid catalytic cracking process using self-optimizing control and reconfiguration. Schedule 1. Control technique. 2. Process description. 3. Description of the control strategy. 4. Simulation software. 5. Results. Control technique. The design of a SOC system is carried out by first identifying the activate constraint. At the nominal optimum, the cyclone temperature T sub Ci is found to be constrained at the outer limit, 100 Kelvin. Applying the GSOC algorithm as shown in a picture. The perturbation space is first sampling using the Monte Carlo method. The simplifying number is set as north equals 500, which is statistically significant in our case, n equal 500. All sampled conditions are optimized for economic benefit using the input solver. Process description. The fluid catalytic cracking (FCC) process consists of the three steps: reaction, product separation, and catalytic regeneration. On the feed side, crude oil is mixed with hot recycled catalytic from the regeneration, and the combined materials are fed to the riser. The heat contained in the catalyst preheats the materials to a certain temperature, proving the energy for oil vaporization and cracking reaction. Along the riser, the heavy oil is broken down into the lighter hydrocarbons during the reaction. The catalysts are deactivated by a mixture of compounds coke left on their surface, so they are returned to the regeneration to burn the deposition coke so that activity is restored. In the regenerator, the catalyst is kept fluid in the rising air. Description of the control strategy. The obtained control variables will be implemented using the SOC retrofit approach, which proposes to the configure and the independent SOC layer on the top of the existing control system, so that the process economics are improved. The motivation for SOC retrofit are, for example, 1. For chemical plants that have already been in operation, there are always feasible regulatory control systems in place. For example, in this study, we intend to improve the economic performance of the FCC process based on the existing configuration, which can be preserved. 2. The use of combination of measures as controlled variables is still difficult for engineers to accept, particularly for field operations who have been familiar with the meaning of individual variables. 3. Safe operation and stabilization remain the first priority for operating chemical plants. This can be well ensured in the upright SOC structure by simple addition saturation blocks for the set points of the controlled regulate variables so that a reasonable operating region can be maintained. The upper and lower setpoint limits can be determined based on experience gained from the historical operation. Basically, they all perform reasonable tracking of their own CPs in the presence distribution. For example, in the Higgs structure, figure 5, the activate constant TCI is maintained around the 1999.5 Kelvin so that TCI is lower than 1000 Kelvin. It's mostly satisfied. The dynamic tracking performance of the three cases are shown in the figure 5, 6, and 7, res- respectively. The results indicate that the weight fraction of the coke in the regenerate catalytic C sub RC is of K important of the SOC, the zinc. For the FCC unit, catalytic regeneration promotes process productivity on the one hand and also consumes energy on the other hand. Therefore, a trade-off is necessary to maximize the economic benefit. Online estimation for unmeasured variables can be performed by the state observers, such as the clamp filter and its variants, subsensors, etc. Development of such sensors, as mentioned, compositional variables can be measured infrequently in practice. Subsensor technique is considered which can be developed in a pure data-driven manner. Therefore, it is more robust to plant model management that are present for the FCC process. Figure compares the true C sub RC and the estimate output given by the LSSBM sensor soft. The results are reasonably good with the average prediction error of about 6%. It is evident that the SOC schemes are closer to the desired optimum. More specifically, the profit function for the three cases are shown in the figure 8. It can be seen that the nominal condition to 0 and 500 minutes, their economic benefits are almost identical and nominal optimal. However, when it comes to the 500 minutes to 2500 minutes scenario, the benefit of Higgs control the structure is about to $42.9 per minute, while the benefits of the COC Shelmes 1 and 2 increase to 43.43 per minute, respectively. In this case, the economic benefit of the COC Shelmen is 1 in slightly worse than Shelmen 2. Further investigation reveals that in this particular scenario, the LSSBM model gives a rather incorrect prediction of CRC, about 15% error. However, If we assume that the LSSBM model is calibrated using a accurate measurement of CRC, the gain increased further to about $43.68 per minute, and is better than the COC Shellman 2.